All right, going to be working here on the homework for 8.6, representing functions as power series. So I'll just remind you that one of the main formulas from this section is this one right here. So if we have an expression 1 over 1 minus u, that can be rewritten as 1 plus u squared plus u cubed forever, which is also represented with this infinite series right here. And this is true so long as the absolute value of u is less than 1. So on number 3, it says to find a power series representation of the function and then find the interval of convergence. So here's a function, f of x is 1 over 1 plus x. We need to make it look like this. So we have an addition symbol here. So instead what I'm going to do is say that this is equal to 1 over 1 minus negative x. And in that case, to match this formula up, the u here for us is this piece right here. So I'm just going to rewrite this. It'll become, this will be equal to 1 plus u, which is negative x, plus u, which is negative x squared, plus negative x cubed plus dot 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 forever, which is the same as sum n equals 0 to infinity of negative x to the n. And this is true so long as the absolute value of negative x is less than 1, which is the same as saying the absolute value of x is less than 1. So an absolute value has the effect of turning that negative into a positive. So that is the power series representation of the function. Let me just double check that that's the way they want you to write it. Yeah, they do say the way that they want it, although that's correct, is to rewrite that power series as follows here. Sum n equals 0 to infinity of negative 1 to the n times x to the n. So that way it looks like your normal power series c sub n x minus a to the n. So your c sub n is this, and this is your x minus a to the n. So that's it. Now the interval of convergence is going to be when this absolute value of x is less than 1, which is the same as saying x is between negative 1 and positive 1. So your interval convergence is negative 1, 1. All right, let's take a look at I'll see if number 4 is worth me doing. Yeah, 4 is worth me doing. 4, you have a function f of x is equal to 5 over 1 minus 4x squared. So again, what we'll want to do is try and make this look like the 1 over 1 minus u and figure out what u is. So I have 1 minus u. This looks like I could use this for u, except for the fact that we have a 5 on top. So I'm going to pull that 5 out front and make it look like this. Like that. So this is our u. So this is equal to 5 times this right here turns into 1 plus u plus u squared plus u cubed plus dot 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 dot, which I could actually simplify this. This would be 1 plus 4x squared plus 16x to the 4th plus, what is that, 64x to the 6th plus dot dot dot. That goes on forever. Sorry, I forgot. That 5 will distribute through to each one of these. But that's just 5 times the power series n equals 0 to infinity of, let's see, our u is 4x squared to the n. And I'll put that 5 back in. So this is sum n equals 0 to infinity of 5 times Now I'm going to do 4 to the n times x squared to the n. So I just split this up into 2. The n only affects the first, or the n is affecting the 4 and then the x squared. And let's see again if that's what they're wanting the final version to look like. Yeah, they go a little bit further. So that's equal to, let's see, sum n equals 0 to infinity of 5 times 4 to the n times x to the 2n. And all they're doing there is just multiplying 2 times n to get 2n. And that will converge so long as this piece right here, which was right here, so long as u was less than 1, the absolute value of it. So from that we can do a little more work. We can take the 4 out, and we can divide both sides by 4, and then we can really at this point you can take the square root, because this is the same as the absolute value of x squared less than 1/4. So that means absolute value of x has to be less than 1/2 when you take the square root on both sides, which means that x has to be between -1/2 and +1/2. So your interval of convergence is -1/2 to 1/2. And this is your power series representation right there. All right. Next, let's see what else we got here. Number 5, yeah. Number 5, 2 over 3 minus x. And remember what we're trying to get it to look like is 1 over 1 minus u. So again, the 2 on top, we don't like that, so I'm going to rewrite that as 2 times 1 over 3 minus x. And then to match this formula, I need a 1 here. So what I'll do is on the bottom, I'm going to factor a 3 out. So watch. When I pull a 3 out, I'm left with a 1. But then I have to pull a 3 out of this, so minus 1/3 x. So if you distribute this back through, you get 3 minus x. And then I'll pull that 3 out on the bottom underneath the 2. So make that 2/3 times 1 over 1 minus 1/3 x. And now you can see I have this piece right here. There's my u, right? So what I'll do is I'll just rewrite it like this. 2/3 sum n equals 0 to infinity of u, which is 1/3 x, to the n, which I can rewrite as 2/3 sum n equals 0 to infinity. I'll just split this up, 1/3 to the n, and then times x to the n. And that's the power series representation. I could put the 2/3 back in here, but I'll just leave it like that. For the interval of convergence, we need u, which was this. We need the absolute value of that to be less than 1. So I can take the 1/3 out, multiply both sides by 3, and that tells me that x has to be greater than -3 and less than +3, which means my interval of convergence is the interval -3, +3, not including the endpoints. I do see they did one more thing here. Because this is a 3, let's just take a look at this. This would be correct for me. I'd be happy with this answer on a test, but because this is a 3 and this is a 3 down here, we could leave the 2 out there. I could bring a 1/3 back in, then I have 1/3 to the n, then x to the n, and then when I look at these two multiplied together, that's to the first power. I can put these, since they have the same base together, I add the exponents. So I have a 2 out here, sum n equals 0 to infinity of 1/3 to the n plus 1 times x to the n. And the book answer goes even just a little bit further. They say, all right, well, if you raise 1 to any power, it's 1. And on the bottom, 3 to that power is 3 to the n plus 1, then times x to the n. So they just use the fact that when you raise 1 to any power, it's still going to be 1. So they split this up into two fractions, or they separate, they do the power on the top and the bottom separately. It's all the same. All right, let's look at number 6. 6, well, I'll do 6. One over x plus 10. Well, first of all, that's the same as 1 over 10 plus x. And I'm doing that because I'm trying to get it to look like this. And I almost have it, except I need a minus here, and this needs to be a 1. So let me first make this a 1. I'll factor a 10 out of the bottom. I'll be left with 1 plus 1/10 x. And that's the same as 1/10 times 1 over 1 plus 1/10 x. And then I'll try and make this a minus, so I'll say that this is 1/10 times 1 over 1 minus negative 1/10 x. So minusing a negative or subtracting a negative is the same as addition. And so now this looks like 1 over 1 minus u. So u is this right here. So this becomes 1/10, and now I'm going to convert this into a power series. Sum n equals 0 to infinity of u, which is negative 1/10 x, that's u to the n. And then I'll split this up. This is 1/10 sum n equals 0 to infinity. And then I'm going to rewrite this as negative 1/10 to the n times x to the n. I'll go a little bit further now. I'm going to rewrite this as 1/10 times sum n equals 0 to infinity of splitting this up because there's a negative there. I'm going to make it a negative 1 to the n, and then I'm going to have a 1/10 to the n, and then x to the n. I only did that to peel that negative off so I can move this one back in, and I'll put it right there and multiply it. And all that does is changes this negative 1 to the n times 1/10 times 1/10 to the n times x to the n. And I can put these two together, which will give me sum n equals 0 to infinity of negative 1 to the n times 1/10 to the n plus 1, and then x to the n. And I'm guessing I can go a little bit further here to try and make it look like the book. Let's see, this right here again, I can split it, this power on 1, this power on 10, and 1 to any power is 1, and then this will be on top, so watch, it'll be negative 1 to the n over 10 to the n plus 1 times x to the n. Now let's see if that's what they have here. This is number 6. Yeah, that's the way they have it, so that's good. Now we need to find the interval of convergence. So remember that the u that we used was negative 1/10 x. We need the absolute value of that to be less than 1. So that turns into, I can do absolute value of negative 1/10 times absolute value of x is less than 1, so splitting that up. Of course, the absolute value of negative 1/10 is 1/10. And then multiply both sides by 10 here. Absolute value of x is less than 10, which means negative 10 is less than x is less than 10, which means our interval of convergence is negative 10, 10. So here's the power series, here's the interval of convergence. Let me see what this text is here real quick. What are we doing here? Number 7. X over 9 plus x squared. All right, so this is the first one that we've seen where we actually have an x in the numerator. So it's going to be very difficult to get it to look like 1 over 1 minus u if our variable is also on the top. So we can still do this. So let's just see. First, I'm going to pull the x out. So just peel that x out and make this 9 plus x squared. And now I have the 1 on top. This I need to be a 1, so I'm going to factor a 9 out. 9, get 1 plus 1/9 x squared. I'm going to pull that 9 out. I'll just place it underneath the x. And then, as that 9 went out under here, I'm going to turn that to a minus. So 1 minus, and then make this a negative 1/9 x squared. So this right here looks like 1 over 1 minus u, where u is this piece right here. So this will turn into, I'm going to leave the x over 9 here, times sum n equals 0 to infinity of negative 1/9 x squared to the n. And we're going to deal with this in just a second, but let's try and clean up what we have there first. So let me clean this up. This is x over 9 times the sum n equals 0 to infinity. All right, so the negative out here I'm going to represent with a negative 1 to the n. The 1/9 I'm going to represent as 1/9 to the n. And then the x squared to the n I'm going to represent as x to the 2n. So that's just all this split up. And now the important step. I'm going to bring this back in here. So when I multiply this x through, it's going to have an effect on that power. We'll see here in a second. I have negative 1 to the n. This n that was on the bottom, I'm going to bring it as a 1/9. Then I already had 1/9 to the n. I had an x to the 2n, but then I just brought in an x to multiply, like that. So now, my sum, negative 1 to the n, I put these two together, that's 1/9 to the n plus 1, and then times, when I multiply these together, there's a 1 there, I add the exponents, x to the 2n plus 1. And we'll probably be able to go one more step on this. I can write that as negative 1 to the n over 9 to the n plus 1 times x to the 2n plus 1. So there's my power series. All I did was what I've been doing before. I did the power on the 1 and the 9, and then the negative 1 to the n on top. So that's our power series. This will only converge when the u, the absolute value of the u, which was this, is less than 1. So I can pull the negative 1/9 out, take the absolute value, so get 1/9 absolute value of x squared less than 1, multiply both sides by 9, and then take the square, 9, and then take the square root, because our next line looks like this. So take the square root, we get absolute value of x has to be less than 3, so negative 3 is less than x is less than 3. That's our interval of convergence, negative 3 to 3. All right, and that was number, what, 7? No, number 7. So let's look at number 8. Well, let's see, do I want to look at 8? 8's done basically the same way as number 7 was done. It's a little bit tricky. Let's look at 8. So for 8, f of x is x over 2x squared plus 1. So I'm going to pull that x out again. I'm going to rewrite this as 1 over, I'm going to flip the order of the bottom, 1 plus 2x squared. And then I'm going to rewrite that bottom as 1 minus negative 2x squared. And now it looks like 1 over 1 minus u. So that becomes, sorry, I had an x in front of that. This x right here. So x times sum n equals 0 to infinity of the u, which is negative 2x squared to the n. Now that's x times sum n equals 0 to infinity. I have a negative, so I'm pull that out. Negative 1 to the n. I have a 2, so 2 to the n. I have x squared, which becomes x to the 2n. And at this point, what I can do is just bring that x back in. So I'll put that x here. And then what will happen when I put these together is I'll add the exponents. So sum n equals 0 to infinity. I'm wondering, I can leave these apart. I'm just seeing if they left them apart or not. Yeah, they did. So negative 1 to the n times 2 to the n, x to the 2n plus 1. So that's my power series. And then what I'm going to do is figure out the interval of convergence. So I need the absolute value of negative 2x squared less than 1. Is the same as 2 absolute value of x squared less than 1, which is the same as absolute value of x squared is less than a half, which means that the absolute value of x squared is less than a half, which means that the absolute value of x is less than the square root of this. So square root top and bottom separately, 1 over root 2. So that means negative 1 over root 2 less than x less than 1 over root 2. So my interval of convergence, I'll put it under here, is negative 1 over root 2, 1 over root 2. And they probably rationalize this. They probably multiply top and bottom here by root 2. Just rewrite this as root 2 over 2, negative root 2 over 2. No, they don't. Wow, that's surprising. I thought for sure they'd do that. All right. That's fine. Okay. Number 9. Oh, 9 looks a little interesting. So we've got 1 plus x over 1 minus x. All so there's a couple of ways you can look at this. Here's the way I'm going to look at it. I'm going to look at this as being, splitting it up into two fractions. 1 over 1 minus x plus x over 1 minus x. So you can do that. You can put this over the denominator plus this over the denominator. Of course, if I add these two together, they have the same denominator, so I just add the tops and I get back to this. If I do that now, I realize that this right here looks exactly like 1 over 1 minus u. This one almost looks like that. So let me do one more thing. 1 over 1 minus x plus, I'm going to pull that x out and then write 1 over 1 minus x like that. So each of these now, I can go right to the power series. So this right here is sum n equals 0 to infinity of x to the n, then plus this one, I have an x out front and then another power series, sum n equals 0 to infinity of x to the n. Now, what can I do here? Look at this. Sum n equals 0 to infinity x to the n, that's this one, plus sum n equals 0 to infinity. When I bring this x back in right here, I add the exponents, I get x to the n plus 1. So my goal now is to try and put this into one series if possible. So let's just look at what's happening here. All right, this is something kind of cool. These almost create the exact same thing. This right here is going to create, if n is 0, I get x to the 0 is 1, then plus, if n is 1, I get x, plus x squared, plus x cubed, plus, and that goes forever. That's this first one. This one right here, so plus, this one right here, if I let n be 0, I actually start at 1. So this is just x plus then x squared, then x cubed, forever. And notice that I can drop the parentheses here, and I have this and this are the same. So those two are the same, added together I get 2 x's. So this is really 2x. I put this x squared and this x squared together, I get 2x squared. And I put this one and this one together, I get 2x cubed. And that'll keep happening. Get 2x to the 4th. But I had a 1 sitting out here. So in front of this, I'm put 1 plus this. So now, let's try and get our heads around what's going on here. This right here, 1 plus 2, and then what you have is x plus x squared plus x cubed plus forever. So I pulled that 2 out just to show you. Okay, I can. Now what is this? Let's try and write that as a power series. That is sum n equals 0 to infinity of x to the n plus 1. So if I start out at 0, 0 goes in here, I get 1. So that gives me this, and then if I let n be 1, I get 2. So this creates this. I have a 2 out in front of it, and then in front of it a 1. And that should be it. Let me see. Yeah. Okay. I like that. That's one way of looking at it. There's several different approaches you can take to this. But the goal is to get one summation, not to have 2 like we had earlier. Even though we have a 1 sitting out in front of that, that's all right. So it's 1 plus this infinite series. Now, still have the question of what's the interval of convergence. Well, we had 2 sums. Both of them, both the sums we had earlier when we started were this, right? We had that, and then the other one was, so we needed the absolute value of x to be less than 1. So you know what the interval of convergence is there. Let's see, let's look at 10. Hopefully 10 will be kind of like this one. Ooh. Not really. f of x equals x squared over a cubed minus x cubed. So a here is a constant, right? This is some fixed number. So what I'll do first is I'll pull the x squared out. Try and turn that into a 1, so I need to factor out an a cubed. That a cubed is going to come out there. And when I pull an a cubed out from here and here, I get a 1 minus, and then 1 over a cubed x cubed. All right, so try it yourself. You multiply this back through the bottom, you get an a cubed, and here to here you get your minus x cubed. So that should work. This right here will be my u. So this whole thing can be rewritten as a power series. And I'm going to write this down up here just so I remember. 1 over a cubed times x cubed. It has to be less than 1 for that to converge. So we have x cubed over a cubed times the sum n equals 0 to infinity of what my u, which is 1 over a cubed x cubed to the n. And then I'll clean that up. I'm going to have x cubed over a cubed times sum n equals 0 to infinity. And then over here I'll split that into 2. So 1 over a cubed to the n, and then x cubed to the n. And now I will put these back in. So the x cubed, I'm going to slide it back here to the end, and the what's going to be left is a 1 over a cubed. I'll put it next to this one. So I have the 1 over a cubed that I just pulled in from out here. I had the 1 over a cubed to the n. I had the x cubed to the n, and I just pulled another x cubed in. So that becomes, was it x cubed or x squared? Hold on. It was x squared. Crap. This was x squared. I just realized that. X squared. This was x squared. So when I put this in x squared, let me just double check that. I don't know why I just realized that. Yeah, that's correct. All right, so when I put these two together, right, get sum n equals 0 to infinity. I get 1 over a cubed to the n plus 1 times, and then over here, remember that this is the same as x to the 3n, and this is x squared, so I add the two powers together. I get x to the 3n plus 2. And then on this one, remember that, I can do the power on the 1 and the bottom separately. So 1 to any power is 1. On the bottom, a cubed. Raising that to the n plus 1, so I multiply. And this is a to the 3n plus 3. When you multiply this times this. And that's on the bottom. So on the top I have this, x to the 3n plus 2. And on the bottom I have this, a to the 3n plus 3. And that's my power series. Now, if you wanted to, you could rewrite it this way. And that would separate out the part that doesn't have x in it, but this is fine. Now, we need to figure out the interval of convergence. So looking back up here, absolute value of a cubed times absolute value of x cubed less than 1. And then I need to multiply both sides by a cubed, absolute value of a cubed. Do they say that a is positive in here? they don't say that A is positive. So we have to be real careful here. A could be negative, which would be a bad thing. So I'm going to try and take this a little slower. I'm going to do this like that. Multiply both sides by the absolute value of A cubed. Right? And then at that point, I can take the cube root on both sides. So absolute value of x cubed less than absolute value of A cubed means absolute value of x has to be less than A. Absolute value. So absolute value of x has to be less than absolute value of A. So this means that this is going to look kind of weird. Negative absolute value of A less than x less than absolute value of A. So that's our interval of convergence. I hope you see that if A is a negative number, I can't have this on this side. Like, I couldn't have this, because what if A is negative? Then that wouldn't make any sense. So I need that. So my interval of convergence is going to be negative absolute value of A, comma, absolute value of A. What are we doing on time? 30. All right. Express function of some power series for you. So 11. F of x is 3 over x squared minus x minus 2. All right, but they tell you in the problem to use partial fractions, so that's a hint. Not sure I would give you that hint on a test, but let me take you through. If you do partial fractions on this, which I'm not going to show, you can rewrite that function as 1 over x minus 2 minus 1 over x plus 1. So what you're doing is you're breaking up the bottom, you're factoring it, x minus 2 times x plus 1, and then you're doing that thing where you're saying that that's equal to a over x minus 2 plus b over x plus 1. Then you're figuring out what a and b are. When you do that, you come back over here, and here's what you get. So now at this point, I try and rewrite these using the formula. So I have 1 over, how do I want to write that? This one right here. How about I write it like this? Negative 2 plus x. The other one minus 1 over 1 plus x. So just flip these over, flip those over. And remember, I'm trying to get it to look like 1 over 1 minus u. So this one should be easy. This one's 1 over 1 minus negative x. All right, minus. Over here, though, let me let me factor out a negative 2. If I pull out a negative 2 on the bottom, I get a 1 minus 1/2 x. Let's see if that works. Negative 2 times this is negative 2. Negative 2 times negative 1/2, that gives me a positive 1x. That should work. So this is really negative 1/2 times 1 over 1 minus 1/2 x. And then this one is minus 1 over 1 minus negative x. So here's a u, and here's a different u. And so now I'm going to have to write 2 power series there. One for each of those. All right, so let's try this. This first one, negative 1/2 times the sum, n equals 0 to infinity of, let's see, u is 1/2 x, so 1/2 x to the n. And then I have minus sum, n equals 0 to infinity. And then here u is negative x, so negative x to the n. Now let's try and get this to look better than that. All right, so check it out. All right, this is negative 1/2. Sum n equals 0 to infinity. This is 1/2 to the n, x to the n, minus sum n equals 0 to infinity of negative 1 to the n times x to the n. Now I'm going to bring this negative 1/2 in like this. So we have negative 1/2, sorry, sum n equals 0 to infinity of negative 1/2 times 1/2 to the n times x to the n minus sum n equals 0 to infinity negative 1 to the n times x to the n. All right, let's put these two together. So how about we do this? Sum n equals 0 to infinity. Now the negative is a problem because this isn't negative, so I'm going to make that negative 1, and then I'm going to have 1/2, and then 1/2 to the n, then x to the n, minus sum n equals 0 to infinity of negative 1 to the n, x to the n. And then I can put these two together. So we've got sum n equals 0 to infinity, negative 1, then I have 1/2 to the n plus 1, x to the n, minus sum n equals 0 to infinity of negative 1 to the n, x to the n. All right. I think I'll do something else here. Gosh, this negative 1, I'm going to take it out and make it like a negative out here, like this. So that's a negative 1 out front. And since these both have negatives in them, I'm going to factor negative 1 out of both. So this is really negative 1 times this sum. And now this negative 1 came out, so it's plus this sum. Like that. All right. And then what I need to do is try and put those two together. So, let's see what I can do here. Since these both have x to the n in common. The only thing that's different is this right here. Then we can do something like this. See if this makes sense within the summation. Let's see if this makes sense. Negative, okay, sum n equals 0 to infinity. So I'm looking at this as if, like this is a common factor. I can pull an x to the n out. And sitting in front of each of those is the 1/2 to the n plus 1, and then over here plus negative 1 to the n. So if I were to distribute this here and here, then I could break it up into two different sums and it would become this. So if I go from here, here to here, I get this. Here to here, I get this. And so I break it in two sums and that's what I get. So this is it. This is good enough. Now that might look a little bit different than the book, but that's good right there. The whole idea is to try and get it into one sum, which I did. Now, interval of convergence, I have to go back and look at my u's. In one of the sums, I had 1/2 x, so I need the absolute value of that to be less than 1. The other one was negative x. I need the absolute value of that to be less than 1. So for this one, I get the interval negative 1, 1. But for this one, I get the interval negative 2, 2. And so for one of the sums to converge, you have to be in here. But for the other sum to converge, you have to be in here. So what we're going to say is that for the whole sum to converge, you need both of them to converge, so we got to go with the smaller interval. So for this series to converge, or the interval of convergence will be this, right there. All right. Give me just a second. They give you the same instructions here that you have to do partial fractions first. So without going into that work, I'm just going to show you this is what you get when you do partial fractions. And then now for each of those, I'm going to try and use the formula. So let's see. I'm going to rewrite this. -1 over 1 plus 2x. This one plus 1 over -1 plus x. All I'm doing is just rearranging things. And I need this to be a minus, so 1 minus -2x. And then over here plus, I'm going to have to pull -1 out of the bottom there. So -1, 1 minus x. Just double check that. This goes to here, I've got this. This goes to here, I've got that. So on that first one, I'm going to pull the -1 out front on the top. Get 1 minus -2x. And then on this one, I'm going to put this -1 out front also. So how about I just say minus instead of -1. 1 over 1 minus x. All right, these two I can represent with power series, and this is u and this is u. So I have it's really annoying. -2x to the n. And then minus another one right here, which will be sum n equals 0 to infinity, and then just x to the n. Which is, let's see, sum. I'm trying to do this one a little different so you can see how it works. I'm going to split this into two, right? Actually into three things, and I'll leave that negative out there, -1 out there. This is -1 to the n, this is 2 to the n, this is x to the n. And then let's say -1 in front of this one, sum, and then x to the n. There's not much going on there. And then the next thing, I'm going to bring this -1 out here in sum n equals 0 to infinity. I have the -1 I just brought in. I had -1 to the n 2 to the n, x to the n, and then minus sum n equals 0 to infinity of x to the n. Now the reason I did that is because I can put these two together. So sum n equals 0 to infinity of -1 to the n plus 1, adding the exponents here, and then 2 to the n, x to the n, and then minus sum n equals 0 to infinity of x to the n. And you can see again, these both have x to the n in them. Since they both have x to the n in them, I can do almost like a factoring, and turn it into one sum. So sum n equals 0 to infinity, and I have some stuff, and then x to the n, which was the common factor in both. Now, here inside I have this, so I need -1 to the n plus 1 times 2 to the n. I need that. That's what was in front over here. And then over here, there's a 1, but then it's subtracted, so I need -1. So you can see now that if I distribute this here and here, and then split it into two sums, I get these two. So that should be it. Good enough. Now what about your interval of convergence? Your two u's were, I think it was what, 2x? Was it -2x? Yeah, it was -2x absolute value, that has to be less than 1. The other one was absolute value of x has to be less than 1. So working with this one, you get absolute value of x has to be less than 1/2, and this one absolute value, well, we're already there here. So this is going to be the smaller of the two intervals. So the interval of convergence for the whole thing will be -1/2 to 1/2. So that's it right there. All right, that's number 12. And I think it's 52 minutes of video, so this is a good point to break. I'll come back and I'll do some more of these. I don't know how many I'm going to be able to get to, but should be enough for now. Okay, I'm working number 13 here from 8.6. So it says use differentiation to find a power series representation for the following. So we cannot get this to look like 1 over 1 minus u because of the squared here. And we can't do partial fractions either. So what we're going to do is we're going to realize that this is actually the derivative of something. So let me start out by trying to show you this. First of all, if I integrate 1 over 1 plus x squared, if I integrate that, make a basic u substitution, u is 1 plus x, du is dx, then this just becomes integral 1 over u squared du. And that's just integral u to the -2 du. And if we find this antiderivative, this will be -u to the -1 plus a constant. And that's just -1 over u. And remembering that u is 1 plus x, we get this. So, all right, so what is this? What the hell does this mean? This means that f of x, this function, is actually the derivative of this. It's the derivative with respect to x of -1 over 1 plus x. So if you take the derivative of this, you get that. We know that because when we integrated that, we got this. So when we do that now, we realize that what's in that parentheses can be written as a power series. So this inside, I'll rewrite that as -1 times 1 over 1. So I pulled that -1 out. Then I'm going to rewrite this as minus -x, like that. And now this piece right here is our u, and I'm going to rewrite that using the summation notation. So we get that f of x is the derivative of -1 times summation -x n equals 0 to infinity, negative x to the n. And then derivative with respect to x of, I'm gonna peel that apart. I'm gonna put the negative 1 inside. Take it easy. Sum n equals 0 to infinity. I have the negative 1 coming in. I have a negative 1 to the n here, and then x to the n. So now this is the derivative with respect to x of, put these two together, right? So that's going to be summation n equals 0 to infinity of negative 1 to the n plus 1, and then x to the n, like that. So at this point, using what we learned about with differentiation of power series, I'm basically going to be using the power rule here. I'm going to treat this as a constant, and I'm going to bring out the n as a power and then reduce the power by 1. And then also remember, because we're differentiating, the index is going to shift from n equals 0 to n equals 1. So taking the derivative now, we get sum n equals 1 to infinity, a negative 1 to the n plus 1 times n x to the n minus 1. So let's see if that's what they want there. So, okay, so now we want to try and find the radius of convergence of this, right? Do they want to know that? That's part A. Find a power series. What's the radius of convergence? So how should we rewrite this? Well, there's a couple of ways. What I'm going to do now is try and get this to be an x to the n instead of x to the n minus 1. So what I want is for my n minus 1 to turn into just an n. So what I'm going to do is I'm going to replace n with n plus 1. So if I replace that n with n plus 1 minus 1, then this will turn into n. So everywhere in the problem, what I'm going to do is I'm going to replace n with n plus 1. So I'm going to rewrite this. Sum, that n right there is going to become n plus 1 equals 1 to infinity. Negative 1, now I replace this n with n plus 1, n plus 1 plus 1. And then I have this n becomes n plus 1. And then this x to the n becomes x to the n plus 1 minus 1. Now, remember, the whole goal was to try and get our power series to have an x to the n and our index starting at 0, and this should do it. Let me write this above here. This is a tricky part of the problem. So, subtract 1 from both sides. Sum n equals 0 to infinity. All right, this is n plus 2, but it doesn't matter if I add 2, if I add 4, if I add 6. That's the same as negative 1 to the n, because when I plug in 0, I get an even number. When I plug in n is 1, I get odd, and the same thing would happen here. If n was 0, it's even. If n is 1, it's odd. So I'm just going to change that to this. If you don't like that explanation, then just rewrite that as this. So this is this, and negative 1 squared is just 1, so it won't matter. Then over here, n plus 1, and then x to the n, right there. So that's our power series. You can see, hopefully, that this part is our c sub n, and this is our x minus a to the n right there. So to find the radius of convergence, we need to do a ratio test on this. So I'm going to take the limit as n goes to infinity of, okay, we plug n plus 1 into this whole thing. So negative 1 to the n plus 1. And then if I plug n plus 1 in there, I get n plus 2. And then x to the n times x. That's this. Now divide that by, or sorry, that's this with n plus 1 plugged in. Then just plug in just n. And so I have n plus 1, then x to the n. I need that to be less than 1. The x to the n's cancel. These don't matter. And so I'm getting limit n goes to infinity. Okay, in terms of n, I've got n plus 2. Here I've got n plus 1. And then an x, I need that to be less than 1. And if you take this limit, this is 1. So you get absolute value of x less than 1, which means our radius of convergence is 1. And our interval of convergence is -1, 1. I don't think they asked for the interval of convergence. Did they? No, they didn't, but all right, that's good. Now, it says, for part B of this problem, it says to find a power series for another function. It's this cubed instead. Well, we just found our power series, right? We just determined that if we have a function, let's call this something else. Let's call this g instead. We know that the function 1 over 1 plus x squared, which is the one we just worked out, was this power series, equals sum n equals 0 to infinity, -1 to the n times n plus 1 x to the n. That's what we know. So that's what we have so far. We want to know what the power series for this one is. So again, what I'm going to do is I'm going to somehow connect these two together using a derivative. So my question to you, or our question to ourselves, is how is this connected in terms of a derivative? So let me differentiate this and see if the derivative of this is that. So what is the derivative with respect to x of 1 over 1 plus x squared, like that? What's that derivative? Well, I can use chain rule. Let me bring the 1 plus x to -2, bring it up like that. So just bring it up. Now let me take derivative. -2 comes out. So this equals -2 comes out, 1 plus x to the -3. So that came out, take the power down, take derivative of what's inside, which is just itself. So this is just equal to -2 over 1 plus x cubed, which is almost that, right? It's almost that. If I pull the -2 out, 1 plus x cubed. So how can I put all this together? Well, what I can say is that if I take the derivative of this, right? The derivative of this is equal to that. So if I take -1/2 times f of x, right? And take the derivative, right? So if I take derivative of this, I get that. Multiply it by -1/2, and I'll get this. So here's what I can do. I can say that this is equal to -1/2 times the derivative of the f function, which is -1/2 times the derivative with respect to x of the f function. What is the f function? The f function is this, written as a power series. There we go. All right, I hope that makes sense. All right. So now let me take the derivative of this power series. Again, this part is our c sub n. We're going to ignore it. We're just going to do power rule. N is going to come out. We're going to subtract 1 from this. This index is going to go up by 1. So this is equal to -1/2 times summation n equals 1 to infinity negative 1 to the n plus 1, and then the n came out times n. Power goes down by 1, and that's it. Okay, so this is a power series representation of this. Now again, what I'd like to do is try and get this to be an n and this to be a 0. So I'll do that same swap that we did earlier. I'm going to take all my n's and I'm going to replace them with n plus 1's. So let's rewrite this power series. This is negative 1/2 summation n equals 1 to infinity. Negative 1, I replace that with n plus 1. And then I replace n plus 1 here, so n plus 2. I replace n plus 1 there, so n plus 1. I replace n plus 1 there, I get n plus 1 minus 1 is x to the n. Oh, sorry, forgot to replace. This was n plus 1 equals 1. So when you do this, subtract 1 on both sides, this is n is 0. All right, looking good, looking good. So now, what I'd like to do is take that negative 1/2 and put it inside, and I'm going to split this negative 1 up right here using that power. So I've got sum n equals 0 to infinity, negative 1/2, negative 1, negative 1 to the n. So that's just splitting this into 2. Then these two, n plus 1, 2 times n plus 1, and then times x to the negative, or x to the n. And I'll put these two together, which will give me 1/2. Sum n equals 0 to infinity of 1/2. I still have a negative 1 to the n. And n plus 2, n plus 1, x to the n. What was this, 13b? All right. Then, part C, it says, now let's look at a different function, different one. H of x is x squared over 1 plus x cubed. So it says find a power series for this one. Well, this is just the same as x squared times 1 over 1 plus x, that quantity cubed. But that's just x squared times this, sum n equals 0 to infinity, 1/2, negative 1 to the n, n plus 2, n plus 1, x to the n. So what I'll do is I'll put the x inside here next to this one. And when I do that, I get sum n equals 0 to infinity of, let's see, 1/2, negative 1 to the n, n plus 2, n plus 1, and then x to the n times x squared, but I'll put those two together and make it x to the n plus 2. And I believe that's all they want for that. Now, if you want to try, I mean, this is fine, but if you want to try and rewrite this so that this is x to the n instead of x to the n plus 2, you're going to have to replace your n's with n minus 2's. So if I put n minus 2 in here, this will be an x to the n. So what I'd like to do is replace all my n's with n minus 2's. So sum, I get n minus 2 equals 0 to infinity, 1/2, negative 1, replace that n with n minus 2. If I do n minus 2 plus 2 here, I get n. If I do n minus 2 plus 1, I get n minus 1. If I do n minus 2 plus 2, I get x to the n. And moving this, adding 2 to both sides on that one, adding 2 here and here, you get sum n equals 2 to infinity. And then here, remember that this really means -1 to the n times -1 to the -2. But this really means 1 over -1 squared. -1 squared is 1. So we don't even need this piece. So that means I don't need to even account for that. So that should work. So that should be the power series representation of that last function. Make sure I've got all that 1/2 in there. Yep. Okay. And then you could do the ratio test and figure out, it doesn't ask for it, but you could do the ratio test and figure out the radius of convergence. All right, that's 13. All right, let's try 14. 14 is going to be similar to this, I think. Let's see. Use equation 1 to find a power series representation for, so 14. It gives you a function, natural log of, where's equation 1? What are they talking about? Natural log of 1 minus x. All right, so let's take a look at that. That definitely doesn't look like 1 over 1 minus u, which is what I need. But notice that if I actually take the derivative of that, I do get this, close to it. So what is the derivative of f? Well, it's 1 over 1 minus x, then times derivative of what's inside, which is -1, which is -1 over 1 minus x. So if the derivative of f is this, and this is something I can turn into a power series, then what I need to realize is that f of x, which is natural log of 1 minus x, is actually the integral of this. So if I take the antiderivative of this, I should get this. Why? Because the derivative of that is this. So working backwards. So what I need to do is just try and figure out how to integrate this. I'm going to turn this into a power series now. So I'm going to write this as integral -1 times 1 over 1 minus x dx. And then here's the thing I can turn into a power series. So I have, let me pull the negative out of the integral. Negative integral. This is summation n equals 0 to infinity of just x to the n dx. So I want to integrate this power series. So when we integrate a power series, we use our general formula that I gave you in class. The big thing about integration is that you do not have to do anything with changing of the index. So realizing in here we have a 1, that's our c sub n, and we use power rule on x to the n. So negative, this equals negative, and then now the antiderivative of this, sum n equals 0, don't change the index, only do that when we're differentiating, and then 1 over n plus 1 x to the n plus 1. The c sub n I just left alone, it's just 1. And I've already done the derivative. Now I do also have to remember I have to add a constant of integration to this. And we're there. Now I'm going to move the negative back in here. I'm going to move it right there. And so I think at this point we can try and change the index over. Let's try and get this to be an x to the n. So I need an n minus 1 there, right? I need to change my n's to n minus 1s. And that will give me an x to the n there. So rewrite the whole thing. I'll do it in red because I'm changing the index. N, changing it to -1 to infinity. negative 1 over, replace that n with n minus 1, so it's n minus 1 plus 1 is n. X to the n minus 1 plus 1 is n, and then of course I still have a constant. And then when you move this, add 1 to both sides, you get n is 1 here. So that would be the power series that represents the natural log of 1 minus x. Okay, negative, let me just make sure I've got everything going here. Yeah, that looks good. All right, so now on the next part of this problem, it says, find a power series representation for a different function. So I'll call this function, I'm going to leave the red one up there. Just remember that this right here equals the natural log of 1 minus x. That's the power series for that. That's what we just found out. So now they want to know for what is the power series representation of the function. I'm going to call it something other than f. I'm going to call it g of what's the power series representation of x natural log of 1 minus x. So all we need to do now is just tack an x onto this. So this will be an x times this series. So the x is going to go at the back. So sum n equals 1 to infinity of negative 1 over n, x to the n times x. But that x can join with this one, n plus 1. And now let's get this to be an n instead of n plus 1. So I'm going to replace n with n minus 1. And when I do that, I get, if I replace that with n minus 1 and add 1 to both sides, I get sum n equals 2 to infinity, negative 1 over, I'm replacing n with n minus 1, so that's n minus 1. X to the n minus 1 plus 1 is just n. So that would be your power series representation of G. Let's see here. They did that a little different. Why did they not? They didn't switch it. Okay. They just left it like this. That's okay though. I mean, this is the same thing, just changing the index. And then, letting x be 1/2 gives natural log of 1/2 equals, I'm not going to do part C. I should go back to part A real quick, just to show you something I didn't show you. How we could find that constant of integration. Remember, we found that natural log of 1 minus x was equal to, where is it? We found that that was equal to negative sum n equals 1 to infinity of x to the n over n, and then plus some constant. Let's try and figure out what that constant is. So what I'm going to do is I'm just going to let x be 0. If x is 0, we get natural log of 1 equals negative sum, and then what happens here? If x is 0, this all goes away, plus a constant. And so if that's all 0, then I get natural log of 1 equals c, but natural log of 1 is 0, so c is 0. So in other words, our constant of integration is 0. So that would be the power series for this. Sorry, I forgot to do that. So we just picked a nice convenient point that we can figure out this side. Like we know that natural log of 1 is 0, so I picked x was 0. And it worked out real nice. We were able to get c. All right. Okay, let's look at number 15. Find a power series representation and determine the radius of convergence for f of x equals natural log of 5 minus x. All right, so let's take the derivative of that real quick. The derivative of this is 1 over 5 minus x times negative 1. And that's equal to negative 1 times 1 over, let's factor out a 5 on the bottom, 5 minus 1/5 x. Trying to make it look like 1 over 1 minus u. I'm working on it. And that's equal to negative 1/5 times 1 over 1 minus 1/5 x. So if the derivative of this is this, then the antiderivative of this is this. So I'm going to try and find the antiderivative of this. I'm going to convert this into a power series. So our original function, right, our original function should be equal to the antiderivative of negative 1/5 times 1 over 1 minus 1/5 x dx. Let's convert this part to a power series. So, and we'll take the negative 1/5 out. Negative 1/5 integral the power series n equals 0 to infinity of this. Here's u, so 1/5 x to the n dx. And then this is equal to negative 1/5 integral sum n equals 0 to infinity of 1/5 to the n times x to the n dx. So I'm about to integrate that power series in there. And I had to peel off to get my c sub n. Here's my x minus a to the n. And so all I have to do is use the power rule for antiderivatives. So I'm just going to go 1 over n plus 1 x to the n plus 1. I'm not going to touch that, and I'm still going to have a negative 1/5 out front. So here, I'm going to go back up to this. Negative 1/5 summation, no more integral because I'm about to integrate. Does not change the index, still stay at 0. And then I have 1/5 to the n, which doesn't change. I have 1 over n plus 1 x to the n plus 1 plus some constant. Now what I'd like to do is bring that negative 1/5 in. So bring that negative 1/5 in. I'm going to leave a negative 1 on the outside. I'm going to peel off the 1/5. I have a 1/5 to the n. I have 1 over n plus 1 x to the n plus 1 plus some constant. And then I'll put these two together, which will give me 1/5 to the n plus 1. And that is a power series representation. Now, my guess is that the book's probably going to want you to turn this into an x. Well, we're going to need to turn this x to the n so we can find the radius of convergence. So to turn this n plus 1 into an n, I'm going to have to replace all my n's with n minus 1. So let's see what happens when I do that. Replace all my n's with n minus 1's. So if I replace that with n minus 1 and then add 1 to both sides, I'm going to start at 1. And then negative 1 just sitting here. If I replace this n with n minus 1, I'm going to get n minus 1 plus 1, that's just 1/5 to the n. If I replace this n with n minus 1, I get n minus 1 plus 1, that's just 1 over n. And then over here, x to the n. And then of course I have a plus a constant. That's it. So that's a power series representation of this. Which one am I doing here? 15. Okay, so let's try and let's try and figure out what our C is, okay? We can do that real quick. Remember, this is what the natural log of 5 minus x is. So let me let x be 0 again. If x is 0, now the reason I'm doing that is because if I let x be 0, this whole thing is 0. So if x is 0, we get natural log 5 equals 0 plus c, which means that c is natural log 5. All right, so I know that that c is natural log 5. All right. Now, radius of convergence. So I'm going to take the limit, then goes to infinity. I'm going to use the ratio test on this. So I get -1, then 1/5 to the n times 1/5 times 1 over n plus 1 times x to the n times x. So that's just replacing all my n's with n plus 1's. And I'm going to divide that by, replace everything, or just leave everything as n. So 1/5 to the n, 1 over n, x to the n. I need that to be less than 1. These will cancel. These are canceled. These don't matter. And we have a fraction over a fraction, so I can flip. And so I'll get something like limit n goes to infinity, n over, now the 5 is still on the bottom here, so I'm going to go 5n plus 5, distributing that 5 through. And then I still had an x over here, less than 1. If I do L'Hopital on that, I'm going to get 1/5, so I have absolute value of 1/5 x less than 1. And then work this out. We've done this several times. You get that. So radius of convergence is 5 because of that right there. Now it doesn't ask for an interval, so I don't need to check endpoints. Okay, I'm going to be working on number 16 from 8.5, I believe it was, or 8.6, I'm sorry. The problem was f of x equals x squared arctangent of x cubed. All right, so what we want to do is we want to write this, find a power series representation of the function. So this definitely doesn't have the 1 over 1 minus u that we've been using. So maybe I can recognize that one of these is somehow connected to this. So just remember, before I get to this problem, the following. That if we had arctangent, excuse me, of x, that this is equal to the integral, or the antiderivative, of 1 over 1 plus x squared dx. So that's something we know from earlier in the semester. And this right here can be rewritten as 1 over 1 minus negative x squared dx, like that. And this right here does have the form of 1 over 1 minus u, where u for us here would be negative x squared. So with that said, I should be able to rewrite this as, not this, I'm not working with this right now, just this. This is the integral of the sum n equals 0 to infinity of negative x squared to the n. And then what I can do is clean that up, the summation, peel things apart. Forgot my dx here. N equals 0 to infinity. I've got negative 1 to the n, and I have x squared to the n, which I'm going to write x to the 2n dx. So at this point, I can use several things to figure out, what the antiderivative of this is. I can use the rule for antiderivatives of a series, and I can just do All right, no more integral. This is equal to some constant plus a new sum. N is still going to start at 0 and go to infinity. Negative 1 to the n doesn't change. But then, be very careful. I have to add 1 to this power and divide through that. So it's by that. So it's going to be 2n plus 1 x to the 2n plus 1. So because we have a 2n up here, we have to pay a little bit of attention to this part. So remember, if we took the derivative, the power would come down. That would cancel. We would reduce the power by 1, and we would get that. Now, I'm going to show you a slightly different way to do that same exact step. That's I don't know if it's easier, but it's a little safer. What I'd like to do is I'd like to take this right here, and I'm going to write out the first few terms of this. So if n is 0, we get a 1 here, we get a 1 here, so we get 1. If n is 1, we get minus, and then we get x squared. And then plus would be the next one, and then n is now 2, so x to the 4th, and then minus x to the 6th, then plus x to the 8th, minus x to the 10th, plus dot, 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 and we're integrating all of that, right? Now if we integrate that, let's integrate these term by term. This will be x, and this will be minus 1/3 x cubed, plus 1/4 x to the 4th. I'm sorry, 1/5 x to the 5th. And then minus 1/7 x to the 7th, plus 1/9 x to the 9th, minus 1/11 x to the 11th, plus dot, dot, dot. And then, of course, there's a c at the end of all of that. So this should give you that same answer, but let's act like we don't know that. Let's try and rewrite this in sigma notation. So what we notice is that it's an alternating series, right? And it starts with a positive. So I'm going to go negative 1 to the n. I'm going to start n at 0. Okay, go to infinity. So that should give me an alternating series starting with the positive. And then notice that this is x to the first power. This is 1/1. So when I plug in 0, I need to get a 1 and a 1. When I plug in 1, I need to get a 3 and a 3. When I plug in 2, I need to get a 5. Oh, I forgot to put 5 here. 5 and a 5. So these are odd numbers. So I need to create the odd numbers starting with 1, but n is going to start at 0. So what I'm going to do is 1/, here's how I create the odds, 2n, and then plus 1. So if I let n be 0, I get 1. If I let n be 1, I get 3. n be 2, I get 5. And then the power will be the same thing, 2n plus 1. And that matches over here, you can see. So there are two different ways to get to this. So let's remember that. If the final result is this, that tangent inverse of x is equal to the integral of this thing, which we said is equal to this. Sum n equals 0 to infinity, negative 1 to the n times 1/2n plus 1, and then x to the 2n plus 1, plus a constant. Now we can actually figure out what that constant is if we just use the fact that if we plug in 0, arctangent of 0 is equal to, well, if all these x's are zeros, then this whole sum is 0, and so we have just plus c. And arctangent of 0, if you just go back to pre-cal, that's 0. So c is 0. So really, we know that this constant is 0. So that is how we can rewrite arctangent of x as this power series. Now let's go back to the original problem. F of x equals x squared times, now tangent of x cubed. What I'm going to do is I'm going to take x cubed here, replace this right here with x cubed, which in this formula would replace this x with x cubed right there. And so what we get is sum n equals 0 to infinity, negative 1 to the n, 1 over 2n plus 1. And then this, when I multiply the 3 times this, I get x to the, 6n plus 3. So 3 times that, 3 times that. So that's what f of x is. Now just move the x squared inside. So when we move the x squared inside, we get sum n equals 0 to infinity of negative 1 to the n times 1 over 2n plus 1. And then times, when we put an x squared out here, we add the exponents, so we get x to the 6n plus 5. All right, so that should be your power series. All right, now you have to find the radius of convergence, so all you have to do is take this right here, absolute value of that less than 1. So I'll let you do that yourself. All right. Let's look at number, what is it, 17? 17. F of x is x over 1 plus 4x, that quantity squared. So if I take that x on the outside and rewrite this like this, I know that I can somehow get this right here to be something like 1 over 1 minus u, because I can look at that as being 1 minus negative 4x. But the squared causes a problem. So let me see if I can somehow connect. Can I connect this to just this somehow? Well, I'm pretty sure that if you take the derivative of this, you're going to get something close to that. Let's see. What would happen if I take the derivative with respect to x of this? So that's the same as the derivative with respect to x of 1 plus 4x to the negative 1. I'm just bringing it up, the whole thing. And then I use chain rule. So negative 1 comes out. And then it's 1 plus 4x to the negative 2 times 4, because you have to take derivative of what's inside. So this is equal to negative 4 times 1 plus 4x to the negative 2, which is the same as negative 4 over 1 plus 4x squared. So you can see that the derivative of this is almost that. Okay? I mean, sorry, the derivative of this is this, which is almost that. So watch what I'll do here. The only difference between this and this is the negative 4. So if I come back and I say now, take negative 1/4 times the derivative of 1 over 1 plus 4x. That will be equal to, so here's the derivative of this is this, and I'm putting a negative 1/4 in front of it intentionally because I know that that's going to turn out to be negative 4 over 1 plus 4x squared, and then these go away and you're left with 1 over 1 plus 4x squared. All right, this is a good thing. All right, this right here is this. I can rewrite this as a power series, and I can differentiate a power series. So now let me come back up here. So f of x is equal to the x we had in front times this, right, which is this. So negative 1/4 times the derivative with respect to x of 1 over 1 plus 4x. That's my original function. And now I'm going to rewrite this with the power series. Let's go ahead and just do it right here. Remember that the plus is the same as minus negative 4x, like that. And so we get negative 1/4 x, I'm just putting those two together, times the derivative with respect to x of the power series, n equals 0 to infinity, of negative 4x to the n. Now there is a radius of convergence that we'd have to worry about, but I'm leaving that to you. You just have to let that absolute value of that be less than 1. So now how do we differentiate this? Well, we first have to peel it apart. So we have to take that negative 1/4 x times derivative with respect to x of sum n equals 0 to infinity of negative 1 to the n times 4 to the n times x to the n. And remember that this piece right here is our c sub n, and then right here, this is our x minus a to the n. So we're ready for the derivative now. And the way the derivative works, the n is going to come down, we're going to subtract 1, the index is going to go up by 1. So we have negative 1/4 x times, no more derivative, n equals 1, because I'm shifting it, because that's what you do when you take the derivative. C sub n does not change, and n comes out, and subtract 1. And then what I'll do is I'll bring, let's see, how should I do this? I'll bring the negative 1/4 in, and well, you know what? Yeah, I'll bring it, and I'll bring the x in. So let me do that over here. So that is equal to sum n equals 1 to infinity. And then when the x comes in and goes next to this x, I add the exponents, I get just x to the n on the outside. And I have an n in front of it. And then I have, let's see, how do I want to do this? How about we look at this negative in front of the 1/4 as a negative 1. And that way when I take this negative 1 and put it times this negative 1 to the n, I add the exponents, I get negative 1 to the n plus 1. And then I get, I need a little more room here, 1/4 times 4 to the n times x to the n, that's where I am. And look at this right here, these two. That's the same as 4 to the n over 4 to the 1, which is 4 to the n minus 1. So I'll go one more line. Sum n equals 1 to infinity, negative 1 to the n plus 1, and then I have 4 to the n minus 1, and then I have x to the n. All right, and let's see if that's what they kept there. All right, that's fine, but they do go and they do switch this index back to 0, which you wouldn't have to do, but let me just do it just to show you that our answer matches the back of the book. So what I'm going to do is try and make this a 0 down here. So I need to put n plus 1 over here so that when I subtract 1 on both sides, I get 0. So I'm going to let all my n's turn into n plus 1s. So I get sum n plus 1 equals 1 to infinity, negative 1 to the n plus 1 plus 1, and then 4 to the n plus 1 minus 1, then x to the n plus 1. So that's replacing all my n's with n plus 1s. Subtract 1 on both sides there. N is 0 to infinity. This right here becomes negative 1 to the n plus 2, and we saw before that this is the same as negative 1 to the n times negative 1 squared. Negative 1 squared is 1, so we don't even care about that. It's just negative 1 to the n. And then here, this is just going to be 4 to the n, and then here, x to the n plus 1. And that, I believe, should match what they have in the back. I left my n out. Shit. I left my n out. Darn it. should have caught that earlier. Right here, when I was rewriting this, there was an n from, remember when we did the differentiation, the derivative. So there should have been an n right here, which meant that there should have been an n, which we replaced with n plus 1 right there. And so next to this somewhere, n plus 1. Sorry about that. All right. That's it. Let's look at 18. F of x equals x over 2 minus x cubed. I feel like I did this in class, but I'm just going to work through it. So I realize I can just split this up, 2 fractions. And I can peel that x cubed off and look at this. And I'm realizing that 2 minus x, I can probably get that to look like 1 minus u. But the cubed causes a problem. So I think that this is the derivative of something, though. If I take the derivative, let's see how close we'll be here. Well, you know what? Let's do it a different way. Instead of guessing what that's the derivative of, let's try a little different. Let's integrate this. So if we integrate 1 over 2 minus x cubed dx, we do a quick u substitution. U is 2 minus x, du is negative dx. Then this integral becomes negative 1 over u cubed du. So I'll let you go through your own work to verify that. That's integral negative u to the negative 3 du. And then using the power rule, we add 1 to this, which gives us negative 2. We have to divide by it. So when we divide negative 1 by negative 2, we get 1/2 u to the negative 2 plus a constant. So derivative of this comes out, turns into a negative 1, got it, u to the negative 3. So that should be it. Yeah, so this is equal to 1 over 2 times 2 minus x squared. That's what that is. So we can't, you know, I want to verify that when we take derivative of this, well, I guess we're okay with all this work, I guess, because we've done it so many times before in the semester. This right here is not this, right? I'm sorry, is not something I can work with. I started with this, I integrated once, I was hoping I could do a power series on that. I can't. So if I integrate that one more time, I should be able to get back to something I can do a power series of. So let me try and integrate now this. So that 1/2 I'm going to pull out, you know, 1 over 2 minus x squared dx. So I'm going through the same thing again. I'm doing a second integration. I'm using the same substitution. And when I do that, I have 1/2 integral. When I rewrite this, this is going to be negative 1 over u squared du, which is 1/2 times the integral of negative u to the negative 2 du. And then when I actually apply the power rule, I get 1/2. Let's see, I need to do add 1 to this, which gives me negative 1. Divide through by it, so that should just be positive 1, u to the negative 1, which is just 1 over 2u, which is just 1 over 2 times 2 minus x. Okay, so what in the world does this all mean? It means that if we take this expression and we differentiate it twice, we should get this. So if we take that expression, differentiate it twice, we should get that. That is something I can do a power series of. So let me just check that what we've done is right. I'm just going to look real quick. I'm going to take this right here. I'm going to take the derivative with respect to x twice, the derivative with respect to x again of 1 over 2 times 2 minus x. So if I do this 2 times, I should get that back exactly. Not that, but just this. So I'm going to rewrite it like this, so it's easier to differentiate. Okay, that's the original one. So let me do this first derivative. I'll still have another derivative we're going to take. But negative 1 comes out, that's negative 1/2. 2 minus x to the negative 2. Then the derivative of what's inside, which is negative 1. When I put this negative 1 and a half together, it just becomes positive 1/2. Now do the derivative again. So when I do derivative again, negative 2 comes out. That's going to be negative 1. 2 minus x to the negative 3 this time, times derivative of what's inside, which is negative 1. These two negative 1s come together to be 1. This is 2 minus x to negative 3, and that is this. So let me see if I can write this out now to make any sense at all. If I rewrite this, I have x cubed times this, which is this right here. So it's the derivative of this, which is, let me write it this way, 1/2 times 1 over 2 minus x. All right, so I just split that apart. The reason I did that is because I'm about to rewrite this using a power series using this thing. But I've got to make it look like that first. So how about we rewrite this x cubed times the derivative with respect to x of the derivative with respect to x of 1 over 4. So I pulled a 2 out of this and popped it out here with this 2. And when I pulled the 2 out, I would have been left with a 1 minus 1/2 x, like that. And now for this piece, I can do a power series. So this is equal to x cubed times the derivative with respect to x of the derivative with respect to x of, let's see, 1/4 is this. And now this is a power series. Sum n equals 0 to infinity of, not negative 1/2, positive 1/2 x to the n. All right, so what do we get here? We get x cubed times the derivative with respect to x of the derivative with respect to x of, let's see, 1/4. How about this 1/4, since it's a constant? Why don't we just pull it out, because the derivative won't affect it. It'll come out and come out. Why don't we just put the 1/4 on the front? And then in here, we have sum n equals 0 to infinity of 1/2 to the n, x to the n. And that's it. It's peeled apart. It's ready for the derivative. So now I'm going to take that derivative. So I have 1/4 x cubed times the derivative with respect to x of, now let me take this derivative. So I have sum, the index is going to come up, n equals 1 to infinity, and then this stays, and then the n comes out, and n minus 1. All right, so there we go. Now, if we're going to do this derivative a second time, what I'm going to need to do is get this thing to be x to the n, not x to the n minus 1. So I need to do a quick switch here. If I want to make that x to the n, I need to replace all my n's with n plus 1s. So if I do that, I'll let you do that on your own. If I replace that with n plus 1, this sum will now start at 0. Go to infinity. It's be 1/2 to the n plus 1. Then it'll be n plus 1 here. And then x to the, when we do that, we get n. And now we can do the derivative again because this is x to the n. And I'm going to get 1/4 x cubed times, no more derivative, sum, index is going to come up by 1 to infinity. And then I have the 1/2 to the n plus 1 doesn't change. The n plus 1 doesn't change. But here the n comes out, then x to the n minus 1. The last thing I'm going to do is, well, I see some stuff I can do with that 1/4. All right, let's push this through now, all right? X cubed is going to go on the end of this, and I'm going to add the exponents. So I'm going to have sum n equals 1 to infinity. At the very end, I'm going to have x to the n plus 2, because when I put x cubed here and add the exponents, I get that. N plus 1 is not going to change. I'll put the n in front of the n plus 1. I'll just switch the order. This is the part that I thought was a little bit tricky. The 1/4 comes in. So I'm going to rewrite 1/4 as 1 over 2 squared. And then, well, you could even write it this way. 1/2 squared, right? That's 1/4. And then this is 1/2 to the n plus 1. And when you add these two together, right, the two exponents, you should get 1/2 to the n plus 3. So sum n equals 1 to infinity, 1/2 to the n plus 3 times n plus 1 times x to the n plus 2. And I'm wondering if they left it like that. They went with an index back, they took their index back to 0. So if I'm going to match the book, I'm going to have to let n turn into n plus 1 and then rewrite it. So let's do that. So this sum, if that's n plus 1 and do the little subtraction, n is 0. Everything's replaced with n plus 1. 1/2, that's n plus 1, so it's n plus 4. And then this is n plus 1. This is n plus 1 plus 1 is n plus 2. And then this is n plus 1 plus 2, which is x to the n plus 3. And that should match what they have. Yeah, they have it written a little different, but I think if you look at the answer in the back of the book, you can tell. They just put, 1 to any power is 1, and then 2 to that power, they just put it on the bottom. So there's your power series. Okay. How are we doing? We got 15 minutes, number 19. Let's see how quickly I can do 19. Ooh, I can't do 19 quickly. Well, no. I don't think I have enough time to do 19 and 20, so I'll have to do another video to do 19 and 20. Okay, I'm going to just talk through number 19 and 8.6. The original function was 1 plus x over 1 minus x squared. 1 minus x, that quantity squared. So what we can do is we can split this into two fractions, the 1 over this and then the x over this, that's this. And then realizing that x can be pulled out in front right here, I'm going to focus all my attention right now on this expression, which appears here and here. And I'm going to realize that that has something to do with the 1 over 1 minus u that I'm trying to get to, except that I've got the squared there. So what I've chosen to do to try and resolve the connection between the two is I'm going to take this expression, I'm going to integrate it. So I do that over here. I integrate this, make a u substitution, u is 1 minus x, du is negative dx, and go through the integral. Rewrite this, bring the u squared up, use the power rule, and then from here I get 1 over u is the antiderivative, replace u with 1 minus x, and you've got this. So this looks exactly like 1 over 1 minus u. So in this case, u is going to be x. So I can always rewrite that as a power series. So therefore, if I take the, since the integral, or sorry, the antiderivative of this, right, is equal to this, that means the derivative of this is equal to that. So the derivative of this is equal to that piece right there. So what I'll do now is I'll rewrite this function, f of x, and instead of writing this, I will write this, which is here, plus, so there's my plus, x, x, and then instead of writing this, again, I'm going to write this right here. And now the 1 over 1 minus x and the 1 over 1 minus x, turn those into the power series here and here. And then at this point, I'm going to differentiate both of these. So when I differentiate this power series, there's no cleaning up that has to happen. The n just comes down, n minus 1 there, and then notice the index goes from 0 to 1. And then I have plus x, and then the derivative here, again, the index changes to 1, n comes down, n minus 1. All right, that's the heart of the problem. Now it's just kind of clean this thing up, get it into one sum. So what I'll do now is I'll take this expression, this x, I'm going to move it in here. When I move it in here, I put it right here. It comes together with this and it changes it to x to the n. This one, nothing changed. Then I'm going to try and make this one x to the n so that these two match. So I have to do that replacement. I need to make this an x to the n power, so I have to replace n with n plus 1. If I do that here, 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 then I will get this right here. And then the other one here I did not touch. So now these both have x to the n's, but the problem is that this one starts at 1 and this one starts at 0. So what I do now is I peel off the first term of this series. So I let n be 0. If I do that, I get 1 x to the 0, which is just going to be a 1. So when n is 0, this is 1. There's that. And then I go n is 1 and to infinity. So this is the rest of it. So that's just peeling that first piece off. Then I still have this second sum sitting here. And notice now both of these have x to the n. And both of these start at 1. So I can put these two sums together. So I can factor out an x to the n. And then I put the coefficient here, n plus 1. I add it, because there's addition here, to this n, and that's right there. When you put those two together, you get 2n plus 1. And your sum goes from n equals 1 to infinity. 2n plus 1 times x to the n, then I have a plus 1 out here. And that's it. That's your power series. Okay, I'm going to try and knock out number 20 from 8.6. Let's see how much I've got to work with here. Now this is the one I started doing in class, but I'm not going to have enough time to finish it up, so I'm going to do it here. We have x squared plus x over 1 minus x, the quantity cubed. So I'm going to first rewrite this as x squared times 1 over 1 minus x, quantity cubed, plus x times 1 over quantity 1 minus x cubed. And so I split it in two fractions and I peeled off the x squared and the x in front. And now I'm going to try and figure out what 1 over 1 minus x cubed is try and get it in terms of 1 over u. So I'm going to take that, I'm going to integrate that. We've done this a few times now, this same technique. U is equal to 1 minus x, du is dx, negative dx. And that means negative du is dx. So I can rewrite this integral negative because of this, and then u cubed du which is going to be integral negative u to the negative 3 du. And then when I do my power rule, I'm going to get negative 1, and then divide by negative 2, so 1/2 u to the negative 2, which is the same as 1 over 2u squared, which is the same as 1 over 2, 1 minus x squared. And now what I'll do is I'll integrate that again. So take 1/2, I'm going to integrate, take the 1/2 out. 1 over 1 minus x, that quantity squared dx. Make the same substitution we made over here. So this will be 1/2 integral of negative 1 over u squared du, which is 1/2 integral negative u to the negative 2 du. And when we do the antiderivative of that, we get 1/2 u to the negative 1, which is 1 over 2, 1 minus x. So in order to get this expression to turn into something that has like 1 over 1 minus u, I'm going to have to, I actually had to integrate that twice to get back to this. That means that if I take the derivative twice of this, I should get this. So that means I'm going to replace this and this with this. So let me do that right now. This becomes x squared times the derivative with respect to x of the derivative with respect to x of 1/2 times 1 over 1 minus x, and then plus double parentheses there, x times the derivative with respect to x of the derivative with respect to x of 1/2 times 1 over 1 minus x. And I'm going to pull the 1/2s out. So let's take that 1/2 out. Take this 1/2 out and put it right here. We can do that because when we take derivatives, the constants just keep coming out. So now I'll rewrite these with the power series. So derivative with respect to x, derivative with respect to x of sum n equals 0 to infinity. And now here u is just x, so x to the n, plus 1/2 x derivative with respect to x of the derivative with respect to x of sum n equals 0 to infinity x to the n. And now I'll actually take the derivative. So 1/2 x squared. I'll do the first derivative. I'm going to have to do it again. The derivative of this is going to be sum, index comes up, n equals 1 to infinity of n x to the n minus 1 plus 1/2 x derivative with respect to x of same exact thing, sum n equals 1 to infinity of n x to the n minus 1. And now let me change these so that these turn into n's instead of n minus 1. So I have to replace that with n plus 1. So what effect does that have? I have 1/2 x squared derivative with respect to x of, if I replace all my n's with n plus 1s, I get sum n equals 0 to infinity this time, n plus 1 there, and then x to the n. And then I'll have the same thing on this one, plus 1/2 x derivative with respect to x of sum n equals 0 to infinity of n plus 1 x times x to the n. All right, give you a second to get all that down. Now I'm ready to take the derivative again. So when I take the derivative again, right, I'll have 1/2 x squared times, now when I do derivative of this, the index will come up, the n will come down, I'll subtract 1. So I'll have sum n equals 1 to infinity. I already had an n plus 1 there. I have an n come down and x to the n minus 1. Then plus a half x sum n equals 1 to infinity. I already had an n plus 1 times n times x to the n minus 1. And now let's get both of these again back to x to the n's. I mean, I could leave it if I wanted to because they both have x to the n minus 1. But, well, let me see what the book does for 20. Well, you know what? Hold on. Before I do that, forgot. I've got to put these x's in. Oops. This x squared is going to come in, and I don't know about the half. Let's just leave the half on the outside of everything. Let's just pull 1/2 out of everything. Let's take this x squared in, so it becomes sum n equals 1 to infinity, n plus 1 times n times x to the n plus 1, because when I bring this x squared in, I add the exponents, and then plus, I pulled the half out, pushing that x in, I get n plus 1 times n, and then x to the n. All right, now I want to try and put these two together, but they do not both have the same exponent, okay, on the x. So now I'm going to try and get that. So I think what I'll do is I'll make them both x to the n powers. So that means I have to change this to an n minus 1. So everywhere I see an n, I'm going to replace it with n minus 1. So if I replace this with n minus 1 and then add 1 to both sides, my sum is actually going to start at 2 to infinity. And then I'm replacing all my n's with n minus 1's. So if I replace n with n minus 1 there, I get n. Replace n with n minus 1, I get n minus 1. Replace n with n minus 1, I get x to the n. And then plus this one I'm not touching. Because it already had x to the n. All right, and then now at this point, I can put these two together because they both have x to the n's, but this one starts at 2, this one starts at 1. So what I'm going to do is I'm going to peel one of these off. So I have 1/2 out here. Sum n equals 2 to infinity, n times n minus 1 times x to the n, plus, so let n be 1, and let's see what we would get here. If n is 1, we get 2 times 1 times x, so just that. And then plus, now the rest of it is the sum 2 to infinity, so I'll just say sum n equals 2 to infinity of n plus 1 times n times x to the n. And now I can put these two sums together, and I can bring this 2x out here to the front. So I have 1/2 2x here plus. Now when I put these two sums together, start my sum at 2 to infinity, it'll be something and then x to the n, because they both have x to the n. So it's just what's in front of this one, which is just n times n minus 1, plus, and then what's in front of this one, which is n plus 1 times n. And I believe we can clean that up. So we have 1/2. You know what, let's distribute this 1/2 through here. This goes to here, we get x plus, now here to here, I'll just put it in front for now. I might need to pass that through in a second. N equals 2 to infinity. And then what do we get here? This is n squared minus n plus, let's see if we distribute n squared plus n. These cancel, and we get 2n squareds. And then we have x to the n right there. Oh, look, and then when we bring that 1/2 in, it kills off the 2. So we should just have this. That's pretty good. All right, let's see if that matches up with what they have here. What number was this? Whoa, I lost my spot here. What number was this? 20? Yeah, that works. They do point out something. I mean, I can point this out. This would be correct, but check this out. This x right here, okay, just x by itself. Notice that if I were to have rewritten this sum, and I started at 1, I know it starts at 2, but what if I started at 1? What would my first term be? If n is 1, I'd get 1 squared is 1, x to the first power. So my first piece would be x, and then plus the rest of the sum, which would go from 2 to infinity of n squared x to the n. And guess what? This is this. So what the book points out is that this can be turned into this sum, starting it at 1 instead of at 2. But that just works out because it works out nice. I mean, we kind of get lucky with that. But this is it. This is what I'd be looking for. Okay, that's number 20. I'm going to stop the video now.